Hey y'all, welcome to Miss Clarke's chemistry class. We are continuing the series on gas laws. We've already talked about the kinetic molecular theory, Boyle's law, Charles's law, and Gay-Lussac's law. Now you can put all those laws together into the combined gas law. That's what we're going to talk about in this lesson. Also, there's going to be some practice problems. Go grab your calculator, notes, something to write with, and let's get started. So let's look at this combined gas law. We've already talked about Boyle's law, which shows us the relationship between pressure and volume, how they're inverse. If one's increasing, the other one's decreasing. Or Charles's law, the relationship between volume and temperature. Remember, that was directly proportional. If one was increasing, the other one was also increasing. And then we had Gay-Lussac's law, which dealt with pressure and temperature. Again, both of those directly proportionate. If one increased, the other increased. Now we're going to look at the combined gas law. Most of the time, teachers aren't going to care that you know this is Boyle's, this is Charles, this is Gay-Lussac. They just want you to know how to work a math problem between pressure and volume, and pressure and temperature, and volume and temperature. I like just memorizing one law, and that's this combined gas law. Because we've got Boyle's, pressure and volume. We've got Charles, volume and temperature. And we have Gay-Lussac, pressure and temperature, all wrapped up into one formula. Let's practice using this. In a couple of the examples, we're going to use all three variables. And then let me also show you how you can use the combined gas law when it's only two of the three variables listed. Okay, let's try our first example. If I have 21 liters of gas held at a pressure of 78 atmospheres and a temperature of 900 Kelvin, what will be the volume of the gas if I decrease the pressure to 45 atmospheres and decrease the temperature to 750 Kelvin? Now, I always recommend going through and identifying all of the variables, especially if the question is really wordy and you read it and you're like, what? Always go back, reread, only looking for the numbers. So we've got 21 liters. That's a volume. I'm going to call that volume 1. 21 liters. And then we keep going. We've got 78 atmospheres. And see how this is all linked together. Of gas, at a pressure of. They go together. So this is atmospheres. That's pressure. Pressure 1. 78 atmospheres. And then we keep reading. And a temperature of 900 Kelvin. So I've got a temperature 900 Kelvin. Now I'm going to keep reading. I've still got more numbers. What will the volume be? Okay, we must be looking for volume 2. Okay, so let's keep going. We've got 45 atmospheres. That must be our new pressure. Pressure 2, 45 atmospheres. And then lastly, temperature also decrease to 750 Kelvin. Okay, so now we're ready to set this up. Now remember that formula was PV over T. PV over T. So my P1 got 78, my V1 had 21, and then my T1, that was 900, my P2, that was 45. We're looking for V2, so I'm just going to call that X. And then over temperature, that was 750. Now there's definitely more than one way to put this in the calculator. If you've learned anything about me, I like to put everything in the calculator at one time. Like I said, there is more than one way. What I like to do is I like to still cross multiply and divide. I'm going to multiply the three numbers that come in a row. So here I've got 78, 21, 75. I'm going to multiply those together. So cross multiply and divide. But when I divide these two numbers, I've got to put them in parentheses. So when I type this into the calculator, I would type in 78 times 21 times 750 divide, open parentheses, 45 times 900, close parentheses. And I am getting volume 2. Okay, so I've got 30 liters. Now, let's go back and look at this math again. You could have multiplied this, divided this, and got you a number and wrote that number here. You could divide this and this, and you could have had a number here, and then you would have had to have brought that other number to get X by itself. You could do all of that. And if you think that's easier, then please do that. I think cross multiplying and dividing is easier. Let's work another problem. A sample of methane, CH4, occupies a volume of 350 milliliters at 25 degrees Celsius. and it exerts a pressure of 1,020 millimeters of mercury. If the volume of gas is allowed to expand to 500 milliliters and 298 kelvins, what will the pressure of the gas be in atmospheres? Okay, so again, I'm going to reread that problem, paying attention to just the numbers, okay? Milliliters, 350 milliliters, that's a volume. Volume 1, 350 milliliters. Temperature, that's 25 degrees Celsius, and I need it in Kelvin, so I'm going to go ahead and add 273. 25 plus 273, and that's 298 kelvins. All right, and then I keep reading. We've got a pressure, but that's in millimeters of mercury. Pressure 1, we've got 1,020 millimeters of mercury. I'm going to keep reading. If the volume of the gas is allowed to expand, okay, volume 2, 500 milliliters, and we've got a new temperature, T2, 298. What will the pressure of the gas be in atmosphere? So we're looking for pressure 2. But it does say in atmosphere. So we've got two situations here. We need to convert this pressure here into atmospheres. Let's do that first. Okay, so I'm going to set my little problem up. I'm going to remember, I need to scoot that up just a little bit. Okay, I'm going to remember that we had 1 atmosphere. That was equal to 101.3 kilopascals. That was equal to 14.7 pounds per square inch. That was equal to 760 torr. That was equal to 760 millimeters of mercury. Millimeters of mercury, that's what I need. Bring that down, because dimensional analysis stays the same no matter what. Millimeters of mercury on top, millimeters of mercury on bottom. We need it to be in atmospheres. I'm going to put atmospheres up top. I'm going to go find 1 atmosphere, put a 1 here, 760 millimeters of mercury, and then let's figure that out. We got 1020 divided by 760. This pressure 1 in atmospheres is 1.3 atmospheres. The other thing that I wanted to point out is we have our temperature 1, that was 298 Kelvin. Temperature 2, that was 298 Kelvin. The temperature stayed constant. So if we are looking at our formula, and I'm going to grab us a little bit more space. So if we've got this formula, PV over T, those are our 1s, PV over T, those are our 2s. Okay, so if we look up here, back up here, if we can still see that, hopefully we can. We've got our pressure, our volume, that's different. So we are going to include volume. Our temperature is the same. We don't need temperature, but we do need pressure because that's what we're solving for. So we can just ignore temperature on both sides and have pressure times volume equals pressure times volume. Let's fill that in. Our pressure 1, that was 1.3 atmospheres. Our volume 1, that was 350 milliliters. Now, it's okay that we're using milliliters because we're using the same unit on either side, as long as it's the same. Let's go to the other side. We're looking for pressure 2, volume 2, we've got 500. So we need pressure 2 by itself, so we're going to divide 500. So our pressure 2 equals, so we have got to put in the calculator 1.3 times 350 divided by 500. And I'm getting the new pressure to be 0.91 atmospheres, which makes sense because if we're dealing with pressure and volume, they're inverses of each other. The volume increased, so we would expect the pressure to decrease. Let's work another example. 1 liter of a gas at standard temperature and pressure is compressed to 473 milliliters. What's the new pressure of the gas? Okay, so let's go through again. I like to identify everything. So we've got 1 liter. That's volume 1, 1 liter. Now, standard temperature and pressure. That means we do know temperature 1 and we do know pressure 1. Standard temperature, that's 0 degrees Celsius. 273, that's just 273 kelvins. And then standard pressure, that's 1 atmosphere. Let's keep reading. The gas is compressed. Here we've got a new volume. So volume 2. Now see, this is in milliliters. 473 milliliters. 1 liter has 1,000 milliliters. That's 3 zeros here. So I could just move the decimal and say that's 0.4 0.73 liters. Ugh, I know. What's the new pressure? And it doesn't mention anything about temperature, so we didn't really need temperature. So if we're looking at our combined gas law, so we don't have to memorize all of the laws, PV over T equals PV over T, except for we just decided we were not going to use T, so we've just got PV equals PV again. So let's fill that in. Pressure 1, that's 1 atmosphere, times 1 liter. Pressure 2, that's what we're solving for. I'm going to put an X. Volume 2, 0.473 liters. We need to get X by itself, so we're going to divide 0.473. So we've got 1 times 1. I don't know why I'm putting that in the calculator. That's just 1. And then divide that by 0.473. And so our pressure 2 is 2.10 atmospheres. I was having to look at sig figs. Got 3 sig figs here, 3 sig figs here. I needed 3 sig figs in my answer. Okay, let's do one last example. I have made a thermometer which measures temperature by the compressing and expanding of gas in a piston. I have measured that at 100 degrees Celsius, the volume of the piston is 20 liters. What is the temperature outside if the piston has a volume of 15 liters? Let's go through and identify all of our numbers. Our first number, we get a temperature, T1. That's in Celsius, so let's go ahead and add 273 to get 373 kelvins. Okay, and then our next number, 20 liters, that's a volume. Let's say volume 1, 20 liters. Let's keep going. What is the temperature? So temperature 2, we don't know. And then the volume 2 is 15 liters. So again, if we're going to use the combined gas law, PV over T equals PV over T. Let's say we've got temperature, yep. Volume, yep. We don't need pressure. So we can just cross it out and don't use it. Pressure must have stayed constant. Volume is on top, so I'm going to put 20 on top. Temperature is on bottom, so 373 on bottom. We're looking for temperature 2, so that X could go on bottom, and then 15. So again, we are going to cross multiply and divide. 373 times 15 divided by 20 equals. Everything up here had 1 sig fig. I'm getting 279, but if I'm going to round that to 1 sig fig, then I could just say that that temperature is 300 Kelvin.
Now you should feel very confident. You should be able to read a problem, figure out what gas law to use, or just use the combined gas law and make it work anytime you need to use a gas law. You're still waiting for ideal gas law, Avogadro's law, or gas stoichiometry. Those are coming. Make sure you subscribe so you don't miss them. Until next time, bye y'all.